First, I want to thank y'all for having me here. I came here last year for the first time, and I'm not part of the, or I wasn't part of the privacy community, but I had such an awesome time. I was so impressed with everyone here, and I want to thank Nuria and Lawrence and the whole organizing team for putting together such a welcoming and just an amazing space. I just was totally blown away, and you know, I brought my co-founder with me as well because it's just a great community. Okay, so today I'm going to talk about A/B testing. Surprisingly, I'm not going to be talking about differential privacy, and this is going to be this is privacy light, so I do appreciate everyone being warm and welcoming because this is going to be a little bit adjacent, but hopefully I think it'll be pretty interesting. It's going to be an applied talk. It's not going to be particularly theoretical. Although, since we are talking about A/B testing, I do think maybe there is a duel, I think, between Pearson-Nyman hypothesis testing and differential privacy. I'm not exactly sure, but so we'll be talking about A/B testing briefly, so maybe implicitly we'll be sort of talking about differential privacy, but not really. Okay, what I'm going to talk about, I'm going to talk about briefly what A/B testing is. I assume most of us know what it is, but it's always good just to like get everything set up. I'm going to talk about what experimentation programs and like what our software does. We have software for doing experimentation, and so we have clients, and so in a way we're sort of like the data processor in a way, and they're the controllers. And so it's like a little bit of a different dynamic than if you all had your own experimentation program and everything was self-contained. A lot of times clients under like HIPAA, or if they're in financial institutions or in Europe or whatnot, they want to be extremely sure that any information that's flowing to us is not flowing anywhere else. And we actually don't have information that we could like, even if we were to give it out, it would be of a low risk. I'm going to talk about data minimization. So we use data minimization principles in the design of our software. In 2015, we did a re-architecture of the software. We saw, principle 2 of privacy by design, and we try to implement that as much as we could. And then we'll talk a little bit about the cons and benefits. There's always trade-offs, so I'm not being paternalistic here, not saying this is the right way to do it. This is a way to do it that we find is useful for some of our clients. Okay, so what is A/B testing? It's actually pretty simple. There's really two things. This is actually the most important one, although this is like the less sexy one, or the one with less math in it. It's really, we just have a random assignment in order to block confounding. This is actually the most important part of an A/B testing procedure. It's not the stats. The stats are often fairly second order. This is the main thing. The main thing is that we don't want selection bias to confound with the treatment effect. So random selection. And then we want to have some sort of process that can analyze the results and differentiate, or at least to see whether or not it's consistent with noise. And so there's a bunch of statistical procedures that we tend to need to use. Like on the left-hand side, we have, the main thing is really regression. So we're going to use least squares regression. But then there's a bunch of statistical tests, at least on the frequentist approach. So we'll use for univariate cases, we'll use a t-test. And then for multivariate cases, questions would tend to use what's known as an f-test. And I'm going to make the claim that actually you can do all this good stuff on data that you've minimized, on aggregate data, as opposed to having to store the data at the individual level. And so that has a lot of nice properties. Okay, so at a high level, random selection coupled with statistical inference, that's what's going to give you causal inference, and that's what we're looking to do. Okay, so what are the types of things that experimentation programs, what are the tasks that they need to execute on? In the most basic case is to have something to do in A/B test, and underneath the hood, oftentimes it's something like a t-test, and we'll go into that in a little bit of detail, very little bit of detail. But also there's more complex types of questions, and you might want to know if, let's say you're running, you want to know whether or not the size of the image, let's say, and the location on the page, the web page, whether or not which component is more important. So you want to explain what component explains the most of the explainable variance. So there'd be factorial designs, that's usually known as a multivariate test. And underneath the hood, that's usually analysis of variance, and we're going to use F-stats. And then this is tangential, this is actually core, but oftentimes there'll be some sort of related optimization procedure like contextual bandits, and that's usually the type of bundle that software that does A/B testing needs to provide. In addition, there are sort of helper tasks that we often need to use. One is often referred to SRM, or sample ratio mismatch. That's usually is really just checking to see whether or not people have been assigned according to the distribution that we're expecting. And this is really a check, a first level check, just to see whether or not maybe confounding has been broken. And then in addition, we might want to know, let's say we have teams that are running hundreds of A/B tests, and they might want to know whether or not one A/B test is potentially influencing another. So usually a system might want to have some sort of process for doing an automatic check to see whether or not, and alerting whether or not an A/B test is influencing another one. And underneath the hood, that's really something where you might use a nested partial F test. So underneath the hood, we're using regression for almost all of this stuff. So just sort of rolling up data minimization, we try to think of it as just enough data. And this is really where intentionality comes in. And what's nice about data minimization principles is that it really forces the organization to think about, at the margin, what bit of data is going to be required to collect. So you need to state up front what type of information is going to be needed to solve a particular task. And so by data minimization, I'm really referring to Principle 2 as well as Article 5C and 25 GDPR, those concepts of minimizing the individual information that we're collecting, minimizing the granularity of any data element, and then minimizing the linkability. So we're going to talk about this idea of just each A/B test or each experiment is going to have its own separate partition data structure. And that's in contrast to what often happens in data science land or in analytics land, is this sort of just in case mentality thinking, which is the 360 view of the customer, and that's to collect everything, to collect at the finest level of granularity, to collect as much data about the individual as possible. And oftentimes that's really about maximizing optionality. Even though that isn't really made explicit, it's really there's really, often it's driven by fear. So folks are afraid of, they want to minimize regret. It's like, hey, why didn't you collect that if we had it? And also there's magical thinking around all this collection of data. Oftentimes it's almost like the gambler who's losing at the table, and they believe it's that next game where the huge payoff is going to be. I guess you could argue that it's I think maybe around here people might try to argue there's fat tails, and so there's huge payoffs that are lurking in the shadows, and so if you do get that next bit, there's going to be some huge payoff. But the main thing is to be thinking at the margin and asking about the marginal value of complexity, and more data is greater complexity. But it does give you greater degrees of freedom, and so there are cases where you might want to collect more data. But it should be explicit, you should be intentional about it. Okay, so normally how the data is collected in sort of that big table view of the world is that we append the A/B testing assignment to all of our other customer data. But really to solve the A/B testing problem, and this is just, again, this privacy by default. So I'm not saying that one has to do it this way, but just from default, you don't really need to collect all that additional data. Really, we only need these two columns. All I need to have is the treatment as well as the conversion event or the sales event or whatever happens to be the endpoint for the experiment. And so what we can do is we can aggregate it, and if we aggregate it into an equivalence class, here it's a very simple equivalence class. I just have an A and a B, and then I just really need three summary statistics. I just need to have the counts, I need to have the sums of the endpoint, and then the sums of squares. So I just need to also square that. So the first two are really about calculating the mean or average values, and when we have the multivariate case, it's really about calculating the conditional means. And then the sums of squares is really about the variance. That's where the statistical inference comes in. But that's really it, and so now we have this nice little data structure. Okay, so how do you do that? How might you do that? Well, here's one case. This is how we do it in very rough form. So let's say a customer comes to the web page. There's a script tag, but it could be a REST API or it could be some sort of SDK. And then there's a random selection. So they've been allocated A, B, C, or D, or whatever it happens to be. And then state is maintained either in the browser or on our customer server, so we don't have access to it, or on the device, what have you. There's a bunch of options. And then maybe there's additional metadata that is painted onto the response. But at the core, it's just somebody got A. And in this case, maybe they also like music, or they also are in the gold loyalty club, let's say. So that little message has no ID on it. All it has is just that array. Someone got a B, they like music, and they're a gold member. Then that comes to an optional privacy server, which is just a lightweight server that runs on the client side, so we don't have access to it, and that can act as a filter. And there they can also inspect the message and prune anything out. So like, let's say in this case, they don't like the fact that the gold tag is coming to us. They can filter out IP, what have you, so they have complete control of it. And then we just get a message back to our server is somebody got B and they like music. And so internally, we just store the data structure as basically like a pivot table, like an equivalence class. So we just have accumulators. And so the data comes in, we just match where it is in the row, and then we just update the count. Or if a conversion event comes in, we update the sum in the sum of square. So what are the benefits of it? Well, you kind of get KAnon for free in a way, or KAnon-ish for free. It's extremely efficient data storage. It's extremely efficient computation at scale. And as I said before, it encourages intentional thinking, being explicit about exactly what type of data we're collecting and not just collecting everything for its own sake. But again, there's always trade-offs. It does limit some of the statistical methods and approaches that you might want to use. A lot of times you don't really need to use them, but there are certain limits. Anyone out there who's thinking about sort of heteroscedastic, robust standard errors or covariance structures, you probably won't be able to do that. But for simple least squares covariance matrices, this is no problem doing it this way. For this audience, it's obviously that there's no formal privacy guarantees. Maybe you could apply differential privacy onto the end data structure. I'm not really sure. But as it stands, there are no privacy guarantees. And you have loss of optionality. So you've kind of explicitly set up front sort of what the nature of the problem is. It's really kind of more of a just-in-time question. So I think everyone here knows what this is, but the main idea is that you're going to hide in a crowd of familiar people who look exactly the same. So what's really sweet is that it's easy for us to report up to our clients with just a quick lookup. It's just like the min value of K for any given test, and then we can give them the K. Or they could ask, what are the equivalence classes that have a K below some threshold? And so it makes it very easy for them to monitor and just have good situational awareness, being intentional about exactly what type of data they have in their, that we have actually for them. Also, it's very efficient data storage. As I said before, it's bounded. So normally, the database will extend by n. So as each individual user comes in, it's another row. But here, it's a fixed size data structure. So I know a priori how big any of our data structures are going to be. So in this case, if we're going to do like a multivariate test, and I want to do an analysis between two A/B tests, I know the number of rows is going to be limited to 4, and I know I also only need my 3 aggregate statistics. So we already know we have a very small data structure. So even if there was 1 million people who went into the experiments, our data structure is still just this 4x6, 4x5 data structure. So it's quite efficient. Okay, why those 3 aggregate measures? Well, it turns out that those are the only measures you really need to do hypothesis testing and calculating means. So I've just color-coded here, so I have our little data structure, and I've just rewritten the formula for a t-statistic. in terms of those aggregate measures. And so it's just a simple plug and play. So on the denominator, that's the standard error, that's the estimate of the standard error. And again, we can just construct it just from pulling data from our data structure. We don't have to do any real calculation other than some simple addition and subtraction. So it's extremely fast, and it makes us able to do it at scale. But the same is true for the multivariate case. And so actually you can do ordinary least squares from equivalence class tables or these pivot tables. And so I don't show the covariance structure here, but you can see here that especially in experimentation, and if you're collecting data that is categorical, and we do only allow categorical data, and we limit the cardinality of any data element so that the joint cardinality doesn't become huge. You can see that you can construct just by count. So that first matrix, the x prime x matrix, it's what's known as the Gramian matrix. You can construct that as just counts and conditional counts. So we just pull that from the data table, and you can construct the Gramian matrix. And then that inversion is, even though that's O3 or N3, K is quite small. K is just the number of data elements. And because we've applied our data minimization principles, we haven't really collected that many data elements. And again, it's just counts. And then the same is true for x prime y. When we're calculating that, it's just conditional sums. And all that lives already on the table, already aggregated. So normally, if you naively were to construct this matrix, you transpose your data matrix. You probably map it into like a dummy variable encoding, or maybe an ANOVA encoding, and then you'd have to transpose that thing, and then you do a matrix multiply by n by k, k by n by k, and that's pretty big. But here, all of the calculations are basically done. So we can do regression very quickly, and because this is the type of regression that you have to do for, say, like our helper functions for seeing whether or not there's a test interference or whatnot, and we're just using like a nested partial F test here, we have to run 2 regressions for each check, and here it's quite inexpensive. Whereas if you had the data at the individual level, it would be very expensive, and it might be quite difficult, and it wouldn't be bounded. You'd have to have a lot of additional complexity to check to see how big those tables are to make sure you're not out of memory when you're doing that matrix multiplication. And again, I didn't show the covariance structure, but I can show people how that's done if they want, just because I thought it'd be a little bit overwhelming. I guess I would say the main value of experimentation and experimentation programs, and really analytics in general, is that to think about it, it's really to provide a principled foundation for making decisions, to being like explicit, and to be thinking about decisions at the margin. It's not, it's just important that this stuff doesn't get ritualized and just sort of fetishized as like, well, hey, we're doing this thing, look at all these experiments, or look at all this analytics, or how advanced our, the statistics we're doing. The real value of it is to help an organization think through problems, be explicit about their problems, be explicit about the trade-offs between competing alternatives, and to think through about unintended consequences. And data minimization, I think also one of the main values of it is that it helps us be explicit. Again, it's like you have to be conscious up front, and I think even in the privacy by design, the original privacy by design piece, there's a discussion about how more data, richer data is better. And I just think maybe that's not the right way to think about it. I think we should think about what's the marginal value of each additional bit. Like, why would we want to collect it? And if you don't have a good answer for that, then maybe you shouldn't collect it. And that's me. So thank you so much. I really appreciate y'all coming.